Hello everyone. So now at this point in the course on digital system design, we know about the background on how we can sort of start from the basic combinational gates, sequential gates, finite state machines and start to build up towards slightly bigger hierarchical design, right. So far we have been looking at the different ways by which we can sort of build up slightly more complicated modules. Now we are going to take a step forward and say, okay, how does this lead us towards the design of a programmable processor, right? And what we are going to do over here is to sort of look at what does it mean for a processor, something that can perform computations, to be programmable, and how do we go about achieving such a behavior by using digital circuits. So to start with, we are going to take a look at an example of a mathematical equation that perhaps might be something that we might want to solve in the context of a digital circuit design. And over here what we are going to do is to start from the mathematics and move forward to how we might implement something like this in digital hardware. So let's start with an equation that should be familiar from high school, the quadratic equation, right? And essentially what the form of the equation is ax squared plus bx plus c, where a, b and c are constants. Of course, we know that the solution for this, right, is given by, well, there are two roots of the equation. X is minus b plus or minus square root of b squared minus 4ac divided by 2a. Now, this is an example of a well-defined computation, right, ideal for a computer to take care of. And here what we are asking is, how do I build a computer that can sort of systematically go through the process of computing something like this without necessarily sort of pinning myself down to building a completely dedicated hardware whose only purpose is to solve this, right. So in other words, I have an equation of this form. I might also have other equations corresponding to different kinds of roots of other equations, right. I might have expressions that give me the sum of a number of terms in a series. I might have expressions corresponding to various other kinds of mathematical formulations. And I don't want to create custom hardware to sort of calculate each and every one of those. And what we would like to understand is there some kind of a general purpose system that we can build where we can then sort of guide its behavior in such a way that it would be able to perform any one of these computations for us. So to do that, let's sort of break this down into smaller parts, right, and focus on what are the kinds of computations that we need to perform and how might we go about building a custom or a general purpose hardware that could solve a problem like this. So with that in mind, we are going to focus first on the discriminant. Well, the discriminant in this case is just this term, the b squared minus 4ac, right. Part of the reason why I am focusing on the discriminant is that this particular operation, the square root, is something that's a little tricky to implement in hardware. It can be done. There are reasonably efficient implementations that are directly in hardware and can potentially even be done using some kind of a combinational circuit, but they are definitely a bit more advanced than what you would expect in just adders and multipliers, right. So I'm going to focus for now on the discriminant, and well, as long as we can sort of figure out how to take care of the square root, it's actually not too hard to do the rest of it either, right, but we are going to leave that aside for now. So if I focus on the discriminant, then I can sort of further break the operations down like this. Maybe the first thing I would do is multiply b times b, because I need to compute b squared, right. So I don't need a separate sort of squaring hardware. All I need is a multiplication, and by feeding b and b as both the inputs to the multiplier, I should be able to get b squared. Now, of course, this assumes that I know already how to implement a multiplier, and we have sort of looked at how more complex circuits can be built out of simpler circuits. So presumably a multiplier circuit would look something like, you have the partial product generation and then you add up all the partial products, right. And the way that we are doing it is some kind of a hierarchical design, as we have been discussing in the previous videos. And of course, the actual fact of the matter here is that I don't really care how the multiplication is implemented. All that I care about is that there is some way by which I know how to implement the multiplication of two numbers that is a pure hardware solution, right? That's the only thing that I'm assuming. I don't want to sort of bring in and say, oh, I'll use a microcontroller to do this, because, well, I don't know what a microcontroller is at this point, right? I'm trying to build one. So on the other hand, we know that by starting from Boolean algebra, binary arithmetic, we can go to adders, then we can go to hierarchical design, and then we can go to multipliers. So presumably I know how to build a multiplier hardware that can perform B times B. Okay, that same hardware can essentially also be used in order to perform A times C. And of course, over here the sort of simplifying assumption that I am making is that I only want to multiply 2 elements at a time. I am also not going to worry too much about overflow and other such problems over here, because as you will see later, at some point I will need to make a decision on how big are the numbers that I am representing, right? And as you know, if you multiply two n-bit numbers, the product is actually requires up to 2 n bits to store. But well, we don't have that kind of luxury here, right? We want to sort of keep the final result also in n bits, whatever that n might be, because we want to sort of devise some kind of a general purpose hardware, right? Rather than sort of saying, oh, if I multiply, then my result is going to be twice as big, so now I need my storage also to be more, and so on. That complicates matters. Instead, I would say, okay, I'll choose a sufficiently large number representation that most of the numbers I am represented in will fit even after being multiplied and so on, right? And if it doesn't, well, it probably means I need to change my number representation in some way. So we have sort of pushed that problem aside, right? The actual number representation is also not what we are going to concentrate on over here. So I'm assuming that I know how to represent numbers, I'm assuming that I know how to multiply numbers. Once I've got A times C, I can do 4 times A into C, right, where already this A into C has been computed out here. Now, as far as this is concerned, I actually have two options, right? I might choose to go with, well, just use a regular multiplier, just the way that we have done so far, right? After all, A times C is now a known value, and I just have to multiply it once again with the value 4. So that's one perfectly valid approach. The other is to recognize that multiplication by 4 in binary is a very easy operation. All that it means is basically shift the number to the left by 2. Right? Because each time we shift left by 1, we are essentially multiplying by 2. Just like when we shift left by 1 in decimal, we are multiplying by 10. We are changing the place value of all the numbers. So shift left by 2 will give us multiplication by 4. Now we are going to leave this aside for the time being. We are just going to assume that we have a multiplier that can perform 4 into AC. And finally, we have a subtraction, b square minus 4ac, right? Alright, so it looks as though we have now come up with a very systematic approach where we have broken the discriminant computation down into a sequence of 2 input operations that we are all familiar with. Now, by looking at this, we can sort of get the idea that we also need some kind of storage. Now, what is the storage, right? What does it mean for us to talk about storage? The one thing that you can see over here is, well, A, B, C in the first place had to be stored somewhere, right? I need to assume that they are available for my hardware to use as and when required, right? But not just that, the output results that come out, B times B, also needs to be stored somewhere. So does A times C. That in turn is going to be used for the next multiplication, and that product also needs to be stored somewhere, because that as well as the B times B that we did in the first step are going to be used in the last step for the subtraction, right? So the operations produce intermediate results. It's not just that, the operations also assume that they have certain values that are going to be taken from some storage, and we need to basically be able to store these results somewhere. Now when we write a C program, this is precisely where we define variables, right? So in a C program, I might define something like, maybe assuming that all my numbers are ints, for example, I might define int temp1 in a C program and say, okay, now temp1 is a temporary storage, and I'm going to use it to store the result B times B, right? Similarly, I declare another variable temp2, right, and use that in order to store A times C. I declare another variable temp3 and use that in order to store 4 times temp2, right? And finally, I use result equals temp1 minus temp3, right? And in this way, by basically having all of these temporary variables or storage, I am able to come up with the final computation. and that in turn gets stored in this variable called result. Just like when we were talking about C programming, we understand that a variable is essentially a name given to a place that we are using for storing some data. That's exactly the sense in which we are using it here as well. So in software, I would use variables. In hardware, how do I store data? Well, in registers, right? Now we have seen in a previous video that registers form part of the storage, and then of course we can go to memory, right? But for all practical purposes, memory can just be thought of as a much larger or a larger pool of registers from which you can perform any kind of storage that you like. Right? So right now I am just going to assume that I have access to registers as and when I need, and I can use them to store data. Alright, so we can basically see how we are able to break this set of operations down into a set of temporary computations, resulting in a final value that is of interest to us. So now let's look at the kind of hardware that we need for solving this problem, right? Well, so far it looks like we are primarily performing arithmetic calculations, right? So we need some kind of an arithmetic unit. What does that mean? It means that it's some kind of hardware that can perform additions, subtractions, multiplications, divisions. We are not really using all of these operations out here. In fact, if you look at it, we are only performing multiplications and subtraction, and one subtraction for the operation, right? So on the other hand, I'm going to assume that I don't want to necessarily create several different pieces of hardware. I don't want to use 3 separate multipliers. I would rather see if I can get the whole job done with, let's say, 1 multiplier unit, right? Because after all, when I look at this kind of code and think of it in terms of a C program, I can imagine that I am performing one computation, then I am performing the next one, then I am performing the next one, and so on, right? Now, technically this is kind of a circular argument. I am using the concept of a C program in order to explain how a processor can be built in the first place, but you can't run a C program without having a processor, right? But intuitively, hopefully this is not too hard to understand. The basic thing that I'm trying to say is you could potentially just create 3 multipliers in order to perform these 3 computations. The alternative is try and have one arithmetic unit and see whether I can give it the right inputs at the right times in order to perform all the computations that it needs. Okay, so I have an arithmetic unit capable of performing calculations. I also need to have some kind of storage, right? And this I can think of in terms of registers, and this is where the idea of a register file that we have talked about earlier comes into play, right? A register file, well, a memory is also something similar, but a register file, as we will see, is even more useful because it allows us to read multiple values and write a value all within the same clock cycle. Now, apart from all of this, it appears that we will also need some kind of selection logic because I need to decide at any given point in time, am I trying to perform a multiplication or a subtraction, or what else am I trying to do, right? So we need some kind of control signals in order to determine what happens there, and I also need some way to write the results back. Presumably, if the registers are the storage elements that are keeping my values, my input values in the first place, maybe I would also like to save the results back into that same set of registers, but then I need some way of activating the write operation to make sure that the write enable on the correct register is activated such that the data goes in there. So this sort of breaks it down and gives us a clearer picture of what kind of hardware we are likely to need when we are building up this entire system. So as we already mentioned, right, we have this notion of a register bank or a register file, right? And what is it that we are trying to do over here? We need to be able to read certain values from registers with selection, meaning that we need to be able to select which register we want the output from. We then want to perform some kind of computations and finally write values back into some registers. It may or may not be the same registers that we started with, right? But we basically need to be able to select the target register and also enable it on demand, right? So we have already seen this picture, right? We know what a register bank or a register file looks like, right? It's basically a set of multi-bit registers that I'm calling reg 0, reg 1, reg 2, reg 3 over here. If I want to read something out, I basically use a multiplexer, right? And by giving the appropriate inputs select inputs to the multiplexer, I can choose which of these 4 outputs is going to come out on data out. So it looks as though reading out a value from this register bank is fairly straightforward and easy to do, right? Now what about updating a value in the register bank? Here what we do is we take the data in, the value that we want to write, we provide it to all the 4 registers as input, and now we would like to control which of the registers actually changes its value. That's easy. You basically provide a select input to the decoder. So it would be a 2-bit select in this case, and that 2-bit select would get converted into activating exactly one of these 4 enable pins, right, or enable signals. Depending on which of the 4 enable signals gets activated, let's say it was 1 0, this particular register reg2 would have its write enable signal activated, and the data would therefore get written in here, right. So this is the basic structure of a register bank, and well, as you can imagine, over here I have a single data output. I could also have chosen to take all these 4 values out into another multiplexer and had one more output coming over here, right. So I can have 2 register values being read out at the same time, and that's not really much of a problem because all that it means is there's a little extra additional fan out on these pins. They just need reg 0 instead of being connected to one multiplexer, needs to be connected to 2 multiplexers. It does increase the load on this output of the register, and as we have sort of hinted at various points, what that affects is the final propagation delay through the gate, right. So when there are like multiple things that are connected to the same point, what ends up happening is that the propagation delay, the TCQ or output delay of this register, is going to increase. Okay, so let's look at what the Verilog code for this would look like, right. Once again we have seen this, we essentially have a positive edge triggered clock over here, right, and of course in this case I have given an asynchronous reset. You could have omitted this and made it a synchronous reset, which is probably what you would do when you are implementing on FPGAs. But the main thing over here is I want to be able to reset all these registers to known values, and what I do is I essentially write a for loop in Verilog, right. So Verilog allows me to describe the expected behavior, and very nicely it resets all the registers. What ends up happening in practice is that when I write code like this, it implicitly the compiler needs to understand that look, it cannot possibly do this across like multiple clock cycles. So what is actually intended over here is that this for loop gets unrolled, meaning that the registers of 0, registers 1, registers 2, registers 3, all of them, it's as though I have written 4 separate lines of code over here, and at the same time when this clock edge and this reset condition is satisfied, at the same time all the 4 registers are going to get updated to the value 0. Okay. Now what about writing into the registers or changing their value? Here what I do is I first check if the write enable signal is high, and then I say only one of the registers is going to get the value from data in. So implicitly this one line over here, this registers of address is assigned the value data in, is implementing this decoder logic for me, right. So this registers of address gets translated into a decoder and some kind of an extra line out here, which gets combined with the write enable signal and fed to each of these individual registers, so that the net result is that exactly one of them will have its value updated, provided that write enable is high, of course. If write enable is low, none of these values are going to get updated. So that's also a good thing to have, because all it means is by providing a separate write enable signal and by making it 0, I can ensure that my registers remain unchanged in any given clock cycle. That will become useful for us later. Now the readout part of it is even simpler. It just basically says take registers of address. It just translates into putting a multiplexer out here. Okay. So of course the good thing is Verilog allows us very compact representations of all the logic that we have over here. We don't need to explicitly put in a decoder, we don't need to put in a multiplexer. Just simple lines of code, right, allow us to write it in a very convenient shorthand that's easy for us as humans to understand, and can be precisely recognized by the compiler as meaning a decoder and a multiplexer respectively. So now we have storage, right, we have this way of storing values in registers. We have not yet talked about how I am going to load the values into the registers, that comes later. But we want to sort of go about doing this in a systematic way, right? We want to be able to store data in registers. That actually comes considerably later, not immediately now. We want to be able to select these registers and send their values to arithmetic modules. So we know how to select registers, but we would like to have some systematic way by which I can convey that information to my hardware. We also want to be able to send those values as inputs to the arithmetic module, which looks like it's basically a wiring problem. I just need to connect things together. But once I have done that, my arithmetic module also needs to be told what to do, right? I need to say what operation to perform. Is it a multiplication or a subtraction in the case of the discriminant computation? And finally, I know that I have a result and I want to be able to save that result back into a destination register. So once we think about it this way, right, these are our requirements, and what I would like to have is to have one general purpose instruction that I can somehow communicate to this piece of hardware that says, okay, this is how you break things up and this is how you connect everything up together, right? And what we are going to do next is to basically look at how do I go about creating such an instruction.